In this video, I am going to discuss one very important type of numerical, which is basically examiner favorite questions related to MOSFET, and the concept is on the topic which I already discussed in my previous video, that is diode connected transistor of MOSFET. Okay, that is MOSFET as diode connection. Okay, so see, often you can face this type of circuits in the examination. Okay, this may look somehow complicated, but the analysis of this circuit is very easy if you know how to understand or how to handle the numericals related to the diode connected transistor. Okay, so I shall post the link of my previous video where I have discussed the theory of the diode connected transistor in detail. You can check from there. Okay, I shall post the link in the description. Now, let us try to understand how to solve this type of numericals. Okay, this type of numericals, again I am saying, this is very important from the exam point of view for semiconductor device and circuit paper. Okay, so analysis of these circuits are very easy. So just some concepts, 3 concepts you should keep always in your mind to solve this type of numerical. That is concept number 1. That is, whenever you see that is gate is short circuited with the drain, so obviously this configuration is nothing but diode connected transistor. So basically, as you know, the MOSFET will be always in the saturation region in case of this type of configuration. So as the MOSFET always in saturation region, so we can say that the drain current formula is ID equal to half into mu n into COX into W by L into VGS minus VT whole square. Right? Now the concept number 2. Concept number 2 says it does not depend on the number of transistors connected. Suppose let us take, for this particular scenario, let us take n number of MOSFETs are connected in series, like this configuration you can see here. For this configuration, ID1 equal to ID2 equal to ID3 equal to IDN. Okay, and obviously you know ID equal to IS because IG, that is gate current, equal to 0. So obviously this condition is another concept for handling this type of series connection of MOSFET. That is ID1 equal to IS1 equal to ID2 equal to IS2 equal to ID3 equal to IS3 dot dot and so on up to IDN equal to ISN. Okay, why? Quite easy explanation. See, if you observe this connection, see, through this drain current is coming, current is flowing. Now the current will not flow through the gate, because through gate current cannot flow to the MOSFET, or from the MOSFET no current can come outside to the gate terminal, because in between gate and the main body or substrate there is an oxide layer which is basically insulating layer. So obviously Ig equal to 0. So whatever current is flowing through the drain, that will flow through the source. Again same thing for M2 also, current flowing through drain will flow through source. That means through this path, observe the mouse pointer, through this path, that is which is connecting the gate and drain, through this path no current will flow. Right? So basically this is one more concept, and another concept, that is concept number 3, that is for this diode connected transistor MOSFET, what we can see, if the drain voltage is V1, source voltage is V2, then generally for solving MOSFET related numerical, we often need the value of VGS, that is gate to source potential. So VGS for the diode connected transistor equal to VDS, you know from my previous video. So VDS equal to VD minus VS, and if VD equal to V1 and VS equal to V2, we can write VGS as V1 minus V2. Okay, so VGS is nothing but V1 minus V2, or drain potential minus source potential, because VGS equal to VDS for the diode connection of MOSFET. Right? This is concept number 3. With these 3 concepts, now we are ready to solve the series connection of MOSFET numericals. Okay, so directly let us go to example 1. So this is the circuit given, and some data which is required to solve this type of numerical also given. See, 5 volt is connected here, then one resistor R is there, 120 microampere current is flowing through this, as you can see it is already given. Now this is Q2 transistor and this is Q1 transistor. For the Q2 transistor, the drain potential, see, it is given as positive 3.5 volt, and for the Q1 transistor, the drain potential is given as plus 1.5 volt. So obviously, as you can see that this is nothing but diode connection of this is MOSFET connected in series, right? So basically same current will flow through two MOSFET. So basically we can write ID1 equal to ID2, and obviously this current is nothing but 120 microampere, right? So ID1 equal to ID2 equal to 120 microampere. This we can write from the concept 2, right? What is the concept 2? I told you. See, ID1 equal to ID2 equal to IS1 equal to IS2 and so on, right? So basically we can write instantly after seeing this circuit only, we can write this conclusion, that is ID1 equal to ID2 equal to 120 microampere. Fine. Now this data is given in the question, that is VT, that is threshold voltage for these two transistor, for this 2 NMOS is given by 1 volt. Mu n into COX is given by 120 microampere per volt square. Lambda is given as 0. That means you no need to consider the channel length modulation. Okay. And L1 and L2, that is the channel length for this 2 NMOS transistor is given as 1 micrometer. Okay. Now they want from what is the what are the values you have to calculate? Number one is W1, that is width for this Q1 transistor, and W2, that is the width of the gate, you can say, for the Q2 transistor, and what is the R, that is what is the value of this resistance R. Okay, so basically let us go one by one. So just take the Q1 transistor. So draw it separately. If you draw separately when you are considering a particular transistor, then obviously you will not get any confusion. Okay. So to avoid confusion, I always suggest to draw a transistor part separately. So basically, see, if you take only the Q1 part, you can redraw like this one, where in the drain we are providing 1.5 volt positive potential, source is grounded, and gate is short circuited with the drain. So basically, from the concept 3, I told you how to calculate gate to source potential, that is VGS for the diode connection. That is VGS equal to VDS, that is nothing but VD minus VS. And here for the Q1 transistor, VD equal to plus 1.5 volt and VS equal to 0. Substitute that and you can get VGS equal to 1.5 volt. Okay. So basically, as you can see that you can again recheck VGS equal to 1.5 volt and VT equal to 1 volt. So obviously VGS is greater than VT. So obviously this MOSFET will be in on state, not in cutoff. And as the gate is short circuited with the drain, so obviously this is saturation region, because you know for this diode connection, obviously VDS is greater than VGS minus VT, because for the diode connection VDS is equal to VGS. So if we subtract one positive value from VGS, so it will result into VDS greater than VGS minus VT. Fine. So obviously this transistor is in saturation region, and obviously channel is found because just now I explained VGS is greater than VT. VGS is 1.5 volt, VT is 1 volt. So obviously this is in saturation region and the MOSFET is on. Now as this is diode connected MOSFET, so obviously saturation region current formula is applicable. So from the concept 1, I told you ID equal to half into mu n into COX into W by L into VGS minus VT whole square. Now our aim is to calculate the width W for this NMOS, right? So ID, that is drain current which is flowing through the Q1 MOSFET. I already told you from the concept 2, ID1 equal to ID2 equal to 120 microampere, right? So substitute that ID equal to 120 microampere, half into mu n into COX. Mu n into COX is already given in the question. See here, mu n into COX is 120 microampere per volt square, right? So mu n into COX substitute. Now W by L. W we need to calculate, it is unknown to us, and L value is given. See, L1 equal to L2 is equal to 1 micrometer. Substitute that 1 micrometer into VGS minus VT whole square, right? Now VGS you know as 1.5 volt. VT for this NMOS is given. See, VT is 1 volt, right? Substitute that. So we can get by simplifying, we can get 2 micrometer by VGS minus VT whole square equal to W. So W equal to 2 micrometer by VGS was 1.5 volt we calculated, and VT was 1 volt, which is given in the question. Now if you solve this, you can get W, that is basically the width for the Q1 transistor. So you can write as W1 also, because it is indicating that this W is for the Q1, or this W is for the first MOSFET, that is this transistor, this NMOS, right? So for this NMOS, the W1 by simplifying in calculator you can get as 8 micrometer. Fine. Now our M is not the question is not completed. We have to again calculate the W2, that is width for this Q2 transistor also. So as I told you, draw this Q2 transistor, this highlighted box separately, so that you can have no confusion, right? So if you draw the Q2 transistor separately, you can get this type of configuration. In the drain of the Q2 we are applying plus 3.5 volt, in the source we are applying plus 1.5 volt, and gate is short circuited with the drain. So from the concept 3, as usual, VGS, that is gate to source potential, equal to VDS, that is equal to VD minus VS, that is equal to 3.5 minus of 1.5 volt, that will result into VGS equal to 2 volt. Right? Now as this transistor is diode connection, so obviously ID is saturation region formula we have to apply, that is ID equal to half into mu n into COX into W by L into VGS minus VT whole square, right, from concept 1. Now to substitute the values, 120 microampere equal to half into mu n into COX was given as 120, right, into W by L. L1 equal to L2 equal to 1 micrometer, it was given in the question. So 1 micrometer into VGS. What is the VGS for this Q2? We calculated, that is 2 volt. Substitute that, 2 volt minus VT. VT for both the NMOS was given as 1 volt. Substitute that, so 2 minus 1 whole square. So if you simplify this expression by calculator, you can easily get W equal to 2 micrometer. Fine. So basically this is W2, or width for the Q2, or width for the second NMOS, that is width for this NMOS. Okay. So I hope you can understand up to this. So W1 and W2 we already calculated. Now very simple, we have to calculate the R. We know this potential plus 5 volt, we know this potential plus 3.5 volt, we know the current flowing through the resistor R, that is 120 microampere. We can easily apply Ohm's law and we can calculate the value of the R. What is Ohm's law? E is equal to IR. So R is equal to VVI, right? So draw the circuit separately and you can get this type of configuration. So plus 5 volt, and in the another terminal of the resistor plus 3.5 volt, and through which 120 microampere current is flowing. So R is equal to 5 minus 3.5 volt by 120 microampere, that is 120 into 10 to the power minus 6 ampere, because 1 microampere equal to 10 to the power minus 6 ampere, you all know, right? Now if you simplify this expression by your calculator, you can get the resistance value as 12.5 kilo ohm. Okay, so basically what are the values we are getting? See, this for this circuit, this R is 12.5 kilo ohm, W2 is how much we got? 2 micrometer, and W1 we are getting as 8 micrometer. Okay, so this is how you should analyze this type of series connection of NMOS. Very simple, just you need to remember these three concepts. This is concept 3, where VGS equal to V1 minus V2, that is drain voltage minus source voltage, because for the diode connection of MOSFET, VGS equal to VDS, right? And through all the NMOS whichever is connecting in the series, the IT equal to IS, all the cases, right? And this, as this is diode connection, so obviously this is in saturation, so saturation region current formula will be applicable. This is how you can solve this type of numerical. In my next video I shall show you another numerical based on this type of concept. This type of concepts are very important for the exam point of view, so that I have given the heading examiner favorite question. Okay, so if you practice this type of questions in a very good manner, then there is a huge probability that you can score a very good marks in your MOSFET related portion your semiconductor device and circuit paper. Okay, so this is all for my this video. Thank you for watching.